Welcome back, everybody, to the deep dive. Today we're diving into some really cool research from the University of Edinburgh.
Hmm.
Yeah, and we got both a presentation and a paper all about serverless functions.
Yeah.
Those little snippets of code living out there in the cloud, and they just spring to life when you need them, then poof, disappear back into the ether.
Right.
On the surface, they seem super efficient,
Uh-huh.
but it turns out there's this hidden performance bottleneck, and nobody was really talking about it.
Yeah, that's right. And it all comes down to this phenomenon called lukewarm execution.
Lukewarm execution.
Yeah.
Okay, that sounds kind of intriguing. I'm guessing it's not as cozy as it sounds.
Right.
But before we get into that, maybe just remind us why everybody's so excited about serverless functions in the first place.
Well, the appeal is really their efficiency. I mean, they execute in just milliseconds. They've got this tiny memory footprint,
Uh-huh.
and they're only invoked when necessary.
Right.
So this means that cloud providers can, tram tons of them onto a single server.
Uh-huh.
It's like a bustling city, everybody's sharing resources.
Yeah.
But, just like in any crowded space, things can get a little messy.
Makes sense. So how did these researchers at Edinburgh figure out that this overcrowding, or as you called it, multi-tenancy,
Right.
was actually impacting performance?
Well, they flooded a server with a bunch of functions and focused on a single function's performance.
Okay.
And then they varied the time between uses.
Okay.
So you can think of it like calling up a busy restaurant sometimes, the food's ready instantly.
Right.
Other times you're left waiting while the chef's scrambling around in the back.
And I'm guessing with serverless functions, the longer you wait, the worse the service?
Precisely. The longer the gaps between uses, the worse the function performed.
Okay.
And they saw like 170% increase in CPI.
CPI?
That's cycles per instruction.
Oh, okay.
It's a way of measuring CPU efficiency.
So functions were practically slowing to a crawl.
Right?
But why would a function get slower the longer it sits idle? Shouldn't it be the opposite?
Yeah, that's the mystery of lukewarm execution.
Okay.
So the function's code is loaded in memory, ready to go.
Okay.
But while it's waiting, the CPU has gone and discarded any of that cached data or those optimized pathways that were related to the function.
Huh.
So it's like the chef prepped all the ingredients hours ago,
Yeah.
but then had to clear the counter when the order finally came in.
Right.
Starting from scratch.
Yeah.
Takes time.
So how did the researchers pinpoint the exact cause of this slowdown?
Well, they used what's called a top-down analysis approach.
Uh-huh.
And they looked at performance counters built right into the CPU,
Okay.
which is kind of like having an X-ray view into the function's execution.
Okay.
And the biggest bottleneck they found
Yeah.
was the CPU struggling to fetch instructions quickly enough.
Interesting.
You see, the instructions are stored in memory,
Okay.
and accessing memory is way slower than the CPU actually processing those instructions.
So it's like having a recipe, but each step is on a separate piece of paper and scattered across the room. Yeah, you'd spend more time searching than actually cooking.
Right. To speed things up, CPUs use what are called caches,
Okay.
and those are like mini memory banks.
Okay.
That store frequently used instructions.
Got it.
The closer the instructions are to the CPU, the faster it can access them.
Makes sense.
And there's this hierarchy. You have the L1 cache, which is the smallest and fastest,
Uh-huh.
then L2 and then L3.
Okay.
Surprisingly, it was the larger, slower L3 cache
Really?
that was causing the problem with these lukewarm functions, not the faster L2 cache.
Huh. That's unexpected. Why would the L3 cache be struggling? You'd think with all that extra space it'd be more than enough.
To get to the bottom of this, they analyzed the instructions that were being used by the function.
Okay.
And that's where they had these two key insights.
Okay.
First, they found what's called a high degree of commonality.
Okay.
So even though a function might be called infrequently, the same instructions were used repeatedly each time.
So it's not about the frequency of use, but the consistency of the instructions being used.
Exactly. The second insight was that even though these functions are small,
Uh-huh.
they use a surprising number of instructions,
Okay.
more than the L2 cache could handle, especially when you have it sharing a server with hundreds of other functions.
So the L2 cache was overflowing, forcing the CPU to go searching in the slower L3 cache?
Right.
It seems like they stumbled upon a real opportunity here. If the same instructions I used repeatedly, maybe you could preload them somehow, almost like giving the CPU a cheat sheet.
That's precisely what they thought, and that's how Jukebox was born.
Jukebox. Okay,
Yeah.
that's a pretty cool name. So tell me more about this Jukebox solution.
Well, you can think of Jukebox as like a backstage crew for serverless functions.
Okay.
So when a function runs, Jukebox is taking notes. It's like, okay, here are all the instructions that were used, and it stores that information in main memory.
Okay.
Then the next time that same function is called, Jukebox is right there.
Uh-huh.
It fetches those instructions and preloads them into that faster L2 cache.
So it's essentially anticipating what the CPU needs and making sure it's already available.
Exactly.
It's like having a sous chef who preps all the ingredients beforehand
Right.
so the head chef doesn't have to scramble.
Yeah. Did it actually work, though?
Yeah, did it work?
It worked remarkably well.
Okay.
Jukebox sped up serverless functions by an average of 18%.
Wow.
And that was under heavy interleaving conditions.
Interleaving conditions, meaning?
Meaning like when you have lots of functions all competing for the same resources.
Okay.
It achieved this by predicting and presetching a whopping 85% of the L3 instruction misses.
That's impressive.
And the best part,
Yeah.
it only needed a tiny amount of memory for its record keeping.
That's a pretty impressive improvement for such a seemingly simple solution.
Yeah.
It really highlights how understanding the nuances of these serverless functions can lead to some really clever optimization techniques.
Absolutely. This research shows that we need to adapt our thinking about performance optimization for these new types of workloads.
Right.
They behave differently than traditional applications.
Yeah.
And solutions like Jukebox really demonstrate the potential for innovation when we tailor our approach to their unique characteristics.
It makes you wonder what other performance bottlenecks might be lurking beneath the surface in this rapidly evolving world of cloud computing.
That's a great point. I mean, this is just the tip of the iceberg as we move towards more event-driven architectures.
Okay.
Where, actions are triggered by specific events rather than running continuously.
Right.
We'll need to keep innovating and finding new ways to optimize performance.
It seems like this research has implications beyond just serverless functions. Could Jukebox-like approaches be applied to other areas of computing as well?
Definitely. Anytime you have code that's executed intermittently or unpredictably, this type of prefetching technique could be beneficent.
Okay.
Imagine applying this to areas like machine learning,
Okay.
where algorithms often need to access vast data sets that might not fit entirely in the cache.
So instead of prefetching instructions, you could prefetch the data.
Right. Exactly. By strategically loading relevant data into the cache beforehand, you could significantly reduce the time spent waiting for data retrieval from slower memory, leading to faster execution times and just improved overall performance.
It seems like the core concept of Jukebox, this idea of anticipating and preloading, could be a real game changer in many different computing scenarios.
Yeah.
It highlights the importance of really understanding the specific demands of your workloads to design the most effective optimization strategies.
Exactly. This research is a great example of how thinking outside the box and challenging conventional wisdom can lead to significant advancements.
Yeah.
It reminds us that there's always more to learn and discover in the world of computer science.
Now, before we wrap up, is there anything else about this research that you find particularly intriguing or that you think our listeners should ponder?
One aspect I find particularly fascinating is the potential for cross-pollination between different research areas. We've seen how techniques from computer architecture like cache prefetching can be applied to improve the performance of serverless functions.
Right.
So what other fields could benefit from this kind of cross-disciplinary thinking?
That's a really thought-provoking question. It opens up a whole world of possibilities. Could we perhaps apply machine learning algorithms to predict which instructions or data are likely to be needed next, taking prefetching to an even more sophisticated level?
That's an excellent idea. Imagine a jukebox that continuously learns from past executions
Okay.
and adapts its prefetching strategies based on the specific patterns of the workload that could lead to even greater performance gains and efficiency.
It seems like we've only just begun to scratch the surface of what's possible with this type of technology. It's exciting to think about the potential advancements that lie ahead.
Indeed, this research is a testament to the power of innovation and the importance of continuous exploration in the ever-evolving field of computing.
It's amazing to think how, a seemingly niche area of research, like optimizing serverless functions,
Right.
can have such broad implications for, the future of computing.
It really underscores the interconnectedness of different fields within computer science.
Yeah.
Like a breakthrough in one area
Mm-hmm.
can often spark innovation in others,
Right.
creating this ripple effect of progress.
And who knows what other hidden performance bottlenecks are out there just waiting to be discovered.
Exactly.
It makes you wonder what other clever solutions are out there just waiting for someone to, connect the dots.
Yeah, there's a whole world of possibilities out there waiting to be explored.
Right.
And, research like this reminds us to never stop questioning, experimenting,
Yeah.
pushing the boundaries of what's possible.
Speaking of exploring, we'll be sure to include links to the original research paper and the Beehive project in the show notes.
Yeah.
For any listeners who want to delve deeper into this world of lukewarm execution and jukebox.
We always encourage our listeners to continue their own deep dives and explore these topics further.
Yeah.
You never know what fascinating insights you might uncover.
That's what the deep dive is all about, sparking that curiosity, igniting those aha moments, and empowering you to explore the fascinating world of knowledge and discovery.
We hope this episode has given you a new perspective on serverless computing and the innovative ways researchers are tackling these performance challenges in this rapidly evolving field.
Absolutely. And remember, the conversation doesn't have to end here.
Right.
We'd love to hear your thoughts on lukewarm execution,
Yeah, right.
jukebox, or any other ideas that this research sparked for you.
Feel free to connect with us on social media and share your insights. We're always excited to engage with our listeners and learn from your perspectives.
So until next time, fellow deep divers, keep those minds engaged, stay curious, and never stop exploring. Thanks for joining us on the deep dive.